Swayam Prabha. Digital India. Educated India.
So, we looked at the problem of reaction diffusion in a rectangular slab, okay. And what I want to do is look at the same problem in a different geometry, in a spherical geometry, because typically catalysts are spherical, okay. You can have catalysts of different shapes. In fact, one of the things which people do is they do make catalysts with different shapes, but if the shapes are not conforming to standard geometry, then the solutions have to be done numerically. So, we want to see if we can get solutions analytically, okay, which means you do not have to go and write a computer program for finding the solution, okay. So, we are looking at reaction diffusion in a porous sphere, okay. Again, what are we talking about? We are talking about the internal diffusional resistance, and we are comparing internal diffusional resistance and the reaction rate. So, we are assuming that the external mass transfer resistance is negligible, okay. So, this is comparison of rate. So, what I am saying is no external mass transfer resistance, or the Km, the mass transfer coefficient is infinity, very large, okay. So, there is no resistance in the film which is surrounding the catalyst plate. Normally, you will have some heat transfer coefficient or mass transfer coefficient. So, we are saying heat transfer coefficient is very large, mass transfer coefficient is very large. So, we are not talking about heat transfer, we are only talking about mass transfer, okay. So, Km is infinity. So, what that basically means is whatever is the concentration of the gas in the bulk will be the same as what it is on the surface, okay. So, this means this implies on the surface of the sphere the concentration is equal to the bulk value, okay. And that is the reason we are impose the Dirichlet boundary conditions. So, we use Dirichlet boundary conditions, okay. Now, supposing you were to formulate this problem, I mean exactly the same as what we did before. You have a diffusion term and you have a reaction term. We again are going to say it is only a one dimensional system. We are not going to worry about all three coordinates, okay. So, if you have a porous catalyst pellet, okay, this porous, the only dimension you are interested in is R, because you have uniform concentration. This is Ca bulk here, this is Cas which is equal to Ca bulk on the surface. the concentration of A is the same as the bulk concentration, because there is no mass transfer resistance, okay. And the gas A is going to diffuse into the pellet, and you have all these active sites, all this catalyst is in the this is the catalyst active sites, okay. So, if you want to write the differential equation for this, d E by r squared d by dr of r squared dCA by dr minus k times Ca equals 0. So, basically this is exactly what we wrote earlier for the slab, okay. You had a diffusion term, only thing is the diffusion term was d square C by dx squared. Here it is Laplacian only in one direction, only in the r direction. So, because we are neglecting the thing in the theta and the phi directions, okay, and this is a reaction rate term. What I want you to understand is this reaction rate term is this constant is defined when the rate is on a per unit volume basis, okay. Only when for homogeneous reactions we will define rate on a per unit volume basis, okay, per unit volume of the reaction mixture. And because you are talking about surface reaction, sometimes there are people who like to define the reaction rate on a per unit surface area basis. When you define it on a per unit volume basis, what is the unit of K going to be? 1 by second, okay. And you look at this, you have meter square at the bottom, meter square per second. So, 1 by second concentration, 1 by second concentration, the equation becomes dimensionally consistent. If your reaction rate is on a per unit area basis, some extra term will come in here, okay. So, anyway, it does not matter, one more constant will come in there, maybe surface area per unit volume will come in, okay. So, it does not matter. Now, this is an ODE which has to be solved subject to some boundary conditions. The boundary conditions are Ca is equal to Cas at r equals r, the radius of the sphere, and Ca is bounded at r equals 0, okay. So, we are all set to solve this differential equation now. I can expand this using the product rule, correct, and I will get dE d square by dr squared of Ca. I should have put total d instead of partial derivative, because there is only one direction in which things are varying, okay. And I take the r squared out, I get d square Ca by dr squared plus, what do I get? 2 by r zero. Now, what is dE? This is effective diffusivity. Well, normally when you talk about diffusivity, you talk about diffusion of gas of a species in bulk, okay. But now we are talking about diffusion through a porous network. So, the entire thing is the catalyst pellet is not, the diffusion is not occurring through a bulk gas, it is occurring through a porous network. So, some tortuosity will be there. So, it will be basically different from the traditional diffusivity. So, but we are just saying if you we can look at this mass transfer process as a diffusion process, and so it is not the actual diffusivity which you will have in bulk gas, when you talk about diffusion of benzene in air, you can use the same diffusion coefficient here. Okay. So, that has to be found experimentally, okay, because this mass transfer occurs through a porous network. Okay. So, that is that. Even in the catalytic slab that we discussed, the diffusion coefficient was effective diffusivity because you had porous catalyst. Now, what you observe is, if you look at this differential equation, this is if this differential equation has constant coefficients, okay, then you can look for a solution in the form of e to the power mr, okay. But this equation does not have constant coefficient. This is constant, but there is an r here. So, this equation does not have constant coefficient. So, we cannot do the solution the usual way, okay. And so, this equation has variable coefficients. So, cannot seek Ca as e power mr. In the catalytic, in the slab problem, you had constant coefficients. So, we could get phi square and all that, okay. So, what we have to do is, we will go back to this equation dE by r squared d by dr of r squared dCA by dr minus kCA equals 0, and do exactly what we did last time, which is make it dimensionless, okay. And we are going to define Ca star as Ca divided by Ca surface, which is the same as Ca bulk, and the length scale r star is r divided by capital R, okay. So, you do all that, and I am going to just rewrite this equation. Star minus k times r squared divided by dE Ca star equal to 0. There is a Cas which cancels off, or Cab which cancels off everywhere. There will be a Ca bulk here, and there is a Ca bulk here, and that is non-zero, so it cancels, okay. So, I have done, all I have done is made it dimensionless, and I am going to call this 1 by r star squared d by dr star of r star squared dCA star by dr star minus phi squared Ca star equal to 0, okay. Same thing like I did earlier. There the length, the thickness of the catalyst pellet was your length scale. Here the radius is my length scale. Only thing I have done is change the geometry from slab rectangular to spherical, okay. So, this is phi squared. Phi squared is your Thiele modulus, and this is k times r squared by dE, okay. So, now the boundary condition will be something Ca star at r star equal to 1 is 1, and Ca star is bounded at r star equal to 0, okay. So, how do you go about solving this? I mean, there is a simple transformation which you can make, which can help you convert this to a differential equation with constant coefficients. Okay. So, that is what we are going to do. We are just going to convert this to a differential equation with constant coefficients by making this transformation. So, you have to understand what the underlying motivation is. Okay. So, the simple transformation is I am going to define C as CA star R star. Is that right? Yeah. So, what is CA star? Is C divided by R star. Okay. So, I want to substitute wherever CA star is in terms of C. Okay. So, what I am doing is I am going to rewrite that equation wherever CA star is there, I am going to write in terms of C. So, C is defined as CA star R star. Yeah. So, I have 1 by R star d by d R star. What is this? R star squared, no? What is dCA by dr star? It is d by dr star of C by R star. Remember, this C is a function of R star. Okay. So, you do this product rule or quotient rule, whatever you want. So, all I have done is replace CA star by C. What is this? 1 by R star times C dash minus C divided by R star squared. Okay. This is just remember, CA star is a function of R star. C is also a function of R star. So, CA star is this thing, and I am just substituting for CA in terms of C. Okay. So, what is this? Square d by dr star of R star C dash minus C. Okay. And now you expand this out again. You differentiate this once, I get C dash plus R star C double dash minus C dash. Okay. So, this is a derivative of this, I am just evaluating the derivative, you see this cancels with that, great. And what I am saying is, when you make this substitution, this second derivative term becomes that. So, second derivative term becomes 1 by R star, this square here and this R star times C double dash minus phi squared CA star, that is the other term. I only substituted for the term here. Okay. I only substituted the second derivative term, and I can take this R star here, I get C double dash minus phi squared C equal to 0, because CA star multiplied by R star equals C. So, I take this R star here, I get that. So, what has happened now? Basically, this is the ODE with constant coefficients. This dash represents derivative with respect to R star, Okay. So, C dash is dC by dr star, that is the dash. That the dash here is derivative with respect to r star. So, you can see this is just second derivative minus some constant C. So, I have transformed my earlier equation which had variable coefficients to an equation which has constant coefficients, and so now I can look for solutions of the form e power m r star. Okay. Now, what are the boundary conditions? At r star equal to 1, what are the boundary conditions on C? Because I need I had boundary conditions on C A star, I need boundary conditions on C. Okay. C at r star equal to 1, what is that? If I put r star equal to 1, C A star is 1, C is equal to 1. Is this clear? Because C A star is 1, r star is 1, so C is 1. And at r star equal to 0, what is going to be the boundary condition? If I put r star equal to 0, C A star, remember, is bounded, it is not infinity. Okay, it is a finite value, multiplied by 0 I will get 0. So, the boundary condition is C at r star equal to 0 is equal to 0. Okay. So, this is very similar to what you did earlier in your rectangular slab problem. Okay. And what are the solutions now? So, I have the differential equation, I have the boundary conditions, I can solve. So, I mean, I can do it in exponential and all that, but I am going to do it in hyperbolic functions. Now, that is easier and faster. So, C I am going to seek as A times sine hyperbolic phi r star plus B cos hyperbolic phi r star. So, you can do, I mean, if you are not comfortable with the hyperbolic functions, you can choose e power phi r star plus e power phi r star, e power minus phi r star, and do it, you will get the same result. So, those of you who are not understanding this hyperbolic function, go and do it in exponential and make sure you get the same thing. Okay. Or we can choose A e power phi r star plus B e power minus phi r star. How do I get that? Basically, what am I doing? You can look for solutions. I think I jumped one step. You can look for solutions of the form. So, we seek C as e power m r star. Okay. Hey, this should be at the beginning. We seek e power m r star, the same as what we did in Cartesian coordinates. And then you substitute this here, you get m squared minus phi squared equal to 0. So, m equals plus or minus phi. So, that is what I put. Okay. You get two solutions, right? If you second order equation, you get two solutions, and then you find the constants using the boundary conditions. So, either you choose this and work, or you choose this and work, you should get the same answer. What is the advantage of choosing this? You will see that evaluation of the constants becomes easy. If you choose this, the evaluation of the constants is possible, slightly less, it takes 20 seconds more, that is all. Okay. And remember what I said, sine hyperbolic x is e power x minus e power minus x by 2, and similarly cos hyperbolic. Okay. So, basically it is a linear combination of this. I am writing it as a linear combination of sine hyperbolic and cos hyperbolic. So, now I am going to substitute this boundary condition at r star equal to 0, C is equal to 0. Okay. So, C equal to 0, at r star equal to 0, that means A at r star equal to 0, sin hyperbolic 0 is 0, cos hyperbolic 0 will be 1, okay. So, I mean cos hyperbolic 0 is cos e power x plus e power minus x by 2, at x equal to 0 this becomes 1. So, what I am saying is plus b into 1. So, this implies b is 0, okay. So, I have to find only one constant A. That is what I meant by saying it is easy to find the constants. If I do this, I have to get two equations and two unknowns and to solve, okay. I also know C at r star equal to 1, so I have to put 1 equals A sin hyperbolic phi, okay, because at r star equal to 1, C is 1. So, what do I get? Therefore, C is written as 1 by sin hyperbolic phi times sin hyperbolic phi r star. I found A, I am substituting A back here, B is 0. B is 0, I get that. So, this is C, which is my transform variable. What I am interested in is C A star, right. So, what is C A star? C A star is C divided by R, right. So, this is my concentration profile of the dimensionless concentration. If I plotted C A star was R star, this is what I would get, okay. So, for a particular phi, you in fact what you people should do is you should go to MATLAB or any software and plot this for different values of phi as a function of R, and you will see how the gradient changes depending on phi, and then you will see that for low phi what is the limit, for high phi what is the limit, okay. For low phi you will see it is almost flat, for high phi you will see it is sharply changing. So, only then you will know, otherwise whatever I am saying you should not believe, okay. So, my suggestion is plot this for different phi, because phi is a constant, some positive constant, okay, different phi as a function of r star. So, let r star go from 0 to 1, okay, and you make a plot of this, then you will get an idea, because phi, remember, is the ratio of the time scales for diffusion and reaction, and you will understand how I was saying, what I was qualitatively trying to explain to you, that the concentration will be uniform, concentration will have a sharp change. So, only when you plot this you will know, okay. So, please plot that. So, now what I want to do is next is basically talk in terms of effectiveness factor, okay. Factor of the catalyst eta, okay. So, now how is it defined? Exactly same way like we did earlier. Eta is actual reaction rate on the catalyst divided by the reaction rate when concentration is uniform at CA bulk, because saying CAS is equal to CA bulk. Actually, it should be CAS. CAS, which in this problem is equal to CA bulk. Okay. So, if the diffusion is very fast, I will have CS everywhere inside. Okay. And so, the reaction rate which is actually happening will be almost the same as the denominator. Okay. So, if DE is high, CA is equal to CAS inside the pellet, okay, and eta will be 1. Basically, if D is high, phi squared is low. Concentration will be uniform. Reaction is slow, diffusion is fast. I told you we are looking at comparing two different rates, right. The diffusion rate is very fast, reaction is very slow. So, everywhere inside I can, for all practical purposes, I will have equal to the surface concentration, okay, and that is what you would get when you plot that. So, this reaction rate, so constant in the actual pellet, the concentration will be equal to CS everywhere inside, which is the same as the denominator, okay. This is my reference value. So, basically this is a measure of the internal diffusion resistance that you have, okay. How much resistance is there because of internal diffusion inside the catalyst, that is what we are trying to measure, quantify using eta. Now, one way to do it is, last time what did we do? We found KCA, integrated it, okay. We found KCAS, integrated it, and then we found the effectiveness factor. But this time I am going to use a slightly different approach, okay. The idea is our pellet is at steady state, okay. So, whatever is going to be consumed in the pellet because of reaction, okay, is going to be coming from the surface physically. So, I mean at steady state, what do you expect? If you look at the entire spherical shell, there is a flux of concentration of A coming into the pellet. Whatever is coming into the pellet is going to be reacted, okay. So, what I can do is I can find what the flux is across the surface. If I can find what the flux of the concentration is across the surface is coming into the pellet, that must be equal to the amount that is being reacted, okay, because that balance that you had, the second order derivative equals reaction rate, it is basically telling you whatever is a diffusive flux is being consumed by the reaction at steady state, okay. Now, instead of looking at a thin shell, I am looking at the entire pellet, okay. So, what I am saying is, I will remember this, pellet is at steady state. So, the diffusive flux inside the pellet, inside diffusive flux across the surface R equals R must be equal to, not flux, diffusive, I should say, so mass transfer. Must equal to, because flux means per unit area, okay. So, I don't want to say flux, diffusive mass transfer across the surface R equal to R must be equal to what is consumed by the reaction at, was consumed by the reaction inside the pellet. Okay. So, what I am trying to tell you is I can measure this reaction rate in two ways, and I will possibly show that mathematically also. Okay. But before showing that mathematically, I will just explain to you physically. So, physically I can calculate this. So, numerator can be found using K Ca times 4 pi r squared dr 0 to capital R. This is in dimensional terms. Okay. So, this is the reaction rate, or I am saying it is the same as d dCA by dr at r equals r multiplied by 4 pi r squared. Why is there no minus sign here? Because I am talking about the flux in the inward radial direction. Minus d dc dr is the flux in the outward radial direction. Okay. That is, this is what is coming into the pellet in the negative r direction. Okay. This is the flux in the inward r direction. That is the reason there is no negative sign, there is a plus sign. Okay. So, what I am going to do is I am just going to calculate the numerator. I mean, I can calculate the numerator either this way or this way. Okay. This is what is being consumed in the pellet by reaction, this is what is coming into the pellet, what is coming into the pellet is consumed by the reaction, they are equal. Okay. And so, I will now write eta as d dCA by dr is all dimensional now, okay, multiplied by 4 pi r squared divided by integral 0 to r k CAS times 4 pi r squared dr. Okay. And this flux is evaluated at r equals capital R. This is all in terms of dimensional, I will convert it to dimensionless and I will use the expression which I got for the dimensionless concentration profile. Okay. So, is this clear? Eta is the numerator what is being consumed by reaction, is the same as the diffusive flux coming, diffusive rate coming into the pellet. So, this dE, this is the flux multiplied by area of the sphere, and this is the reaction rate when the concentration is uniform everywhere. Okay. Now, since I got my concentration in dimensionless form, I would like to make this dimensionless, and I can evaluate this because this is CS is uniform everywhere. Okay. This is a constant, this is a constant, and this is just 4 by 3 pi r cube. Okay. So, the denominator is 4 by 3 pi r cube multiplied by k multiplied by CAS, that is the denominator. This is the denominator. What is the numerator? The numerator is d times, I am going to convert this to dimensionless, dCA star, and do that I get a CAS, and I convert this to R star, I get an R here, okay, and this is evaluated at R star equal to 1 multiplied by 4 pi r squared. So, this is d times 4 pi r into CAS dCA star by dr star at r star equal to 1. Okay, that is the numerator. So, basically eta will turn out to be numerator divided by denominator okay. So, now and this is at r star equal to 1. So, what you do is you get rid of things which you can get rid of. So, 3 comes to the thing, 1 r will cancel with this and I get r squared here, and you realize that k r squared divided by the diffusion coefficient is phi squared. So, that is the phi squared here at the bottom. So, I have 3 divided by phi squared, this 3 comes whatever, okay, and the CS also cancels because of first order reaction, and then I have dCA dA star by dr star, okay, at r star equal to 1. This is eta, but I know CS star. Okay. So, CS star was 1 by r star sin hyperbolic phi r star. Okay. That is CS star. We derived that. We found the expression for the concentration inside. So, I need to find the derivative of this. Again, this is a constant, this is a product rule, use that. So, CA star derivative at equals, what is it, minus 1 by r star squared sin hyperbolic phi r star by sin hyperbolic phi plus 1 by r star cos hyperbolic phi r star by sin hyperbolic phi. Is this right? Sin hyperbolic x. So, I have a phi outside, no? Okay. All I have done is differentiated this, remembering that sin hyperbolic derivative is cos, e power mx, m will come outside, so phi comes out. But I have to evaluate this at r star equal to 1. At r star equal to 1, equals, put r star equal to 1 here, you get minus 1 and phi cot hyperbolic phi. Okay. So, basically what this means is eta is nothing but phi cot hyperbolic phi minus 1 times 3 by phi squared. So, okay. So, basically what how is all this useful? You can plot eta versus phi, right, this effectiveness factor. So, for a given system, given reaction, the reaction rate constant is known, K is known. For a given pellet which you have designed, the diffusivity is known, okay, and the size of the pellet is known, R is known. So, if you have a particular system, the reaction rate, the radius of the pellet R is known, K is known, D is known, you can calculate phi squared, okay. And if you have, I mean, if you have to plot this, you will get some value. I mean, I think this is eta equal to 1. In the limit of phi going, you can look at the limit of phi going to infinity, some asymptote will come, okay. I am not getting into them, those details. This is not a course in CRE, but the point is you can calculate phi, because phi is nothing but R times square root of d by K by dE, isn't it? Yeah, phi is this. So, for a given system where you know the size of the catalyst, where you know the reaction rate constant, and let us say you know the effective diffusivity, phi is known, once the phi is known, you can use this graph or use this formula to find the phi, find the eta, and you know how effective the catalyst is. Or ulta, opposite, what you can do, you say, look, I want my catalyst to be 80% efficient, okay. The internal diffusion resistance should not reduce my reaction rate by more than 80%. So, you want your eta to be 0.8. So, if you want eta to be 0.8, you put eta equal to 0.8 and solve for phi. This has to be done numerically using some Newton-Raphson method, or you come to this graph, put eta equal to 0.8, draw a curve, find the value of phi. Once you know the value of phi, if you know what the effective diffusivity is, what the K is, you can decide what should be the size of your spherical catalyst, okay. So, you can use this analysis in different ways. So, at the end of the day, when you do all your calculation and everything, you need to know what exactly are you, how exactly are you going to use it for, okay. So, this is how I can possibly use this analysis that I have done. If you know phi, you can find out how effective your catalyst is. If you want to design your catalyst for a particular effectiveness factor, for a particular efficiency, you fix the efficiency, use this graph and get the phi value, or use Newton-Raphson to get the phi value, and then use that to get R. Because R is the only parameter which you have at your disposal for controlling. Ke for a reaction is constant, you have to change the catalyst, okay, or the effective diffusivity you can't really control too much, okay. So, that is basically how I can use this. The only thing which I want to add at the end is, all along I have assumed my pellet to be isothermal. I have not considered any temperature effect. I am saying that the temperature is uniform inside, temperature is constant. So, K, remember the reaction rate constant is a function of temperature, okay. It depends exponentially on temperature through the Arrhenius kinetics. Now, we have not considered all that, we are just saying, so whatever I have done so far is only valid for isothermal pellets, okay. This analysis, okay, let me just summarize quickly, and then, so this is valid for isothermal pellets, okay, constant temperature. The other thing I want to mention is, for a given catalyst and system, we can find eta, or for a fixed, for a desired eta, we can find phi, either graphically or numerically using Newton-Raphson. This we use to get R, the radius of the pellet. Okay. And finally, if your reaction is exothermic, okay, so it may appear to you that eta always has to be less than 1. Okay. Now, the question is, does eta have to be less than 1? So, for regular reactions, first order, second order, the reaction rate increases with concentration decreases because of diffusion, so effectiveness factor will be less than 1. But suppose you have an exothermic reaction, okay, then inside the reaction heat is going to be liberated, and the temperature inside the pellet, inside the pellet heat is going to be liberated. The temperature inside the pellet can be more than the ambient temperature, and the reaction rate inside the pellet can be more because the temperature is high. So, although the concentration is low, the temperature can be high, and so the reaction rate can be high. So, because of the although you may have a diffusional resistance, the temperature effect may give you a higher reaction rate. So, there can be a situation where eta can be more than 1. Okay. So, eta is going to be less than 1 for typical nth order reactions if it is isothermal, but if it is non-isothermal like an exothermic reaction, okay, we are talking about exothermic reactions, temperature in the pellet can be more than the surface. So, reaction rate can be high because of the temperature. So, here what is happening, concentration decreasing, so reaction rate is low at the center, but temperature can be high if it is exothermic. So, reaction rate can be high. So, you can get a higher reaction rate in the numerator, and you can get a higher effectiveness factor, more than 1. Okay. So, basically keep that in mind. So, for exothermic reactions, temperature at R equal to 0 can be higher than at the surface at R equals R. Okay. So, reaction rate inside the pellet can be high compared to the surface, and so eta can be greater than 1. Okay. That is the only thing you have to remember. Yeah. No. Reaction rate always increases with temperature. Reaction rate will always increase with temperature, no matter whether it is exothermic or endothermic. Reaction rate is given by Arrhenius kinetics. K equal to, this is the reaction rate, K equals K naught e power minus E by RT. Temperature increases, reaction rate increases, it does not matter. So, reaction rate is different, I mean, it is not different, is always going to be increasing with temperature. Okay. If it is exothermic reaction, heat is liberated, temperature goes up. If it is endothermic reaction, heat is consumed, temperature in the plate will be lower. If you are talking about a reversible reaction, then you have a problem. Okay, if you are possibly thinking about a reversible reaction. When you have a reversible reaction, then and if it's exothermic, you have higher temperature, because of Le Chatelier's principle, it will be shifted to the left, and then the conversion may be lower, but as far as the reaction rate is concerned, okay, it will be like this. And the other thing is, whatever I have done is for irreversible reactions. Okay. So, whatever I have done so far is for A giving products, not A giving product giving back A. So, we are assuming everything is irreversible. Okay. Yeah, but if it is reversible, then things become a bit more tricky, because you have a forward reaction, you have a backward reaction, and you have to consider two reaction rates and then do the analysis. Yeah, so reaction rate is irrespective of whether it is endothermic or exothermic, reaction rate will always increase with temperature. Okay. Only thing is, temperature will decrease in the pellet if it is endothermic, because heat is consumed. With exothermic, temperature will increase because it is released. Okay.